Hello, friends. Today I'll tell you what's special about quantum computing and why is it that it is faster than classical computers. I'll show it with an example of the Grover's algorithm. I'll run it through step by step how the Grover's algorithm works and how is it faster than classical search operations. Firstly, we have binary search, which takes log n for sorted arrays, but given unsorted conditions, binary search needs to sort the array or the list first, then we can perform log n time complexity operation of binary search, which makes it n log n for an unsorted, which is the best possible as for the classical computers. Now coming to the quantum computers, we have the Grover's algorithm, which takes root n times to search for a target in unsorted data, which can be a database or a list, anything like that. And it's faster, we can see from the graph itself. Root n is significantly faster than log n. Before we jump into this algorithm, we need to learn a somewhat prerequisites which we need before starting. And that's we all know in a classical world there's this 2-bit 0 and 1. All operations work on those. Whereas in the qubit or the quantum world, we have what we call a quantum state, which is shown like this. It is also called a superposition, where a superposition can have n number of these coefficients, where the only necessity is that all these coefficients should sum up to 1, which is the norm, because we know probability cannot be greater than 1. So it's a must for the superposition. Yeah, so those are the some basics of quantum which we need to know before jumping. Also, I forgot about these. Also, there's this two gate, Hadamard gate and Pauli Z gate, which we need to know. Pauli Z gate is the NOT gate from the classical world, which transforms 0 to 1, 1 to 0. In this gate, in the quantum world, it doesn't do that exactly. What it does is it changes the phase. That is, if suppose the signal is this going up in the positive direction, it changes it to a negative direction. That's basically what the polyZ gate do. It's a form of an oracle operator in the 1 qubit system. For bigger qubit systems, that is 2 or 3 or n such qubit systems, the oracle function becomes much more complex. We'll discuss what's an oracle function later again. And coming to Hadamard gate, this is a normalization tool. That is, suppose we have n states like this. We need to assign similar amplitudes to everyone. So 1 by root 2, it assigns every state's amplitude as 1 by root 2. If we see the graph, we can clearly see that it's uniform. It's all 1 by root 2 after passing through a Hadamard gate. Now we can jump into the structure of a quantum qubit, which is this. If suppose this is the state, this is the psi, then its value must be in some alpha, beta, alpha 2, sorry, it should be 1, in some superposition state, this means. And if it's in up or exactly down, it means 0, means 1. In between means some alpha 1 plus some alpha 2. combination, linear combination. So that's what the graph tells us. Now we can jump into the actual algorithm which works on the circuit diagram. If we follow it carefully, we can easily understand the algorithm. Firstly, what we do is we take two qubits, not necessarily two. We can take a qubit, and what we do is we pass this qubits into the Hadamard gate, which then gives us a normalized state vector where all these states are initialized to a 1 by root 2 amplitude, which is after passing it through the Hadamard gate, initially we get this type of graph, that is the amplitude graph. Hadamard gate helps us to, you know, to measure the states properly with an uniform amplitude to all the states. You can get their basis states easily. Whereas if the coefficients were something else for each and every one, we would have trouble finding what we need because linearity is not maintained. So after passing it through the Hadamard gate, uh, we get this uniform graph, after which we pass it through the oracle function. Now, what does this oracle function do? Its purpose in life is to change the phase of the target. Suppose these all are my states. It will inverse the phase of the target and keep all others as it is. Okay, so this supposed to be this, but after this oracle function, it changed to a negative phase. That's why for a one qubit system, I took this poly operator case, poly Z. But for n qubit systems, where the complexities are very high, we cannot simply just use a poly Z gate to function with it. It will not work. So now, after the oracle function is passed, we again pass the states through the Hadamard gate for normalizing, and after normalizing to so that we can measure actually, we pass it through the diffuser. The purpose of the diffuser is to reflect the mean of the states. What I mean by that is, suppose suppose we have the state here. This is our state. It's in a superposition state of this theta by 2 of 0 plus theta by 2 of 1, as you can see from the diagram. Now, if we find the mean, what would be the mean? The mean would be theta by 2 plus theta by 2, which gives us theta value. And the formula for the reflection is 2 times the mean minus one of their amplitudes. And one of their amplitude, it's not one of their amplitude, since the amplitudes are same for my case, I'm giving it theta by 2. I'm taking any one of the coefficient. But in your case, you would have to calculate for each. That is, for this case, you first have to calculate for theta by 2. Then, if it were theta by 3, you should have to again calculate it using 2 theta minus theta by 3 for each reflection, for each state. Sorry. Now, for my reflection, I can get my reflection as 2 times the theta minus theta by 2, which gives me 3 by 2 theta, which is for this state, if I am considering, it will get shifted towards this. Okay, for this state, it will be shifted towards the zeroth state. Suppose I was finding, suppose if this was my target, that is, I needed to find the state zero. What was the probability that I find the system in state zero? And since my target was also state zero, the amplitude rose. How did it rise? It rised using the diffuser. The diffuser increased the amplitude for which the phase was reversed using the calculation we did just now. So the new amplitude would be 3 by 2 of phi. Sorry, 3 by 2 of theta. This would be the new state. We can now see it's closing in towards zero, which means we are progressing. Now, after the diffuser, after passing it through the diffuser, I can show you the graph. The graph will then become after the oracle function, what it was doing was it simply just inverted the phase. Now, after the diffuser, it will shrink the amplitudes of other amplitudes, which is not my target, and amplify the one which is my target. Why it does so? I clearly showed you now because of this inversion about the mean. Both both these parts make the final diffusion. These two together amplify the target's amplitude and decompose the amplitudes of which are not our targets. So the final diffusion looks somewhat like this. Now here we can see this is reaching towards 1 and the rest part is reaching towards 0. Sorry, 0. So we can see the final superposition state would somewhat look like alpha tending towards 0 and beta tending towards 1. It should be the other way around because as we can see it's tending towards zeroth state. So the zeroth state vector will rise to 1 and the coefficient, that is the amplitude for the one state vector, will go towards 0 from the graph. You can clearly see it. Now after the final diffusion, we again pass it through the Hadamard gate for measuring, and upon measurement we can find whether the target is there or it's not, and after checking if the probability is not high enough, we can reiterate, send it back, it will reiterate, and this time this angle will rise to this using the diffusion, and it will rise and rise, and it will eventually go up to the 1. This means 1 times the state vector 0 plus 0 times the state vector 0 times the state vector 1. This means that means we found the value 0 in the search space, and the number of iteration it takes is uh, root n. After iterating root n times, we will finally get alpha and beta values as 0 or 1. If it's 0, both are 0 means not found. If it's 0 and any one of them is 1, that means it's found. Now we can come to the question of why the Grover's algorithm exactly takes root n steps to complete the search. It's because the amplitudes are equally spread across n states. That is, for a single qubit system it was 1 by root 2, but for an n qubit system it will be 1 by root 2 to the power n, because it's n qubits, so it's rising to the power of 2 to the power n. Now we also know that the n, capital N, is the search space. That is the total number of elements there are we need to find, and the total number of basis states we have is also equal to 2 to the power n. 2 to the power n is the total number of basis states in an n qubit system. So 2 to the power n is exactly equal to n, which is the search space. So we can substitute 1 by root 2 to the power n as 1 by root n. That's why the amplitudes of each state is exactly 1 by root n. And so the target's amplitude will also be initially 1 by root n. Now after each iteration, the psi state moves closer and closer to the 0 or 1th state. How it does so is, suppose we have this is our 2D rotational graph, and this is our initial state where our theta value is 0, because we are uniformly setting each amplitude to be 0, to be 1 by root n. So from here we can see that theta is nothing but equal to 1 by root n. I also have a proof for it down here, that y is theta equal to root n. But simply, if you see, since theta is 0 and initially the amplitudes are 1 by root n, we can say that theta is also equal to 1 by root n. Now for each iteration we are moving towards the target with a deviation of 2 theta. So to maximize our probability, we will need to move it to either this or this, where both of the angles are 90, that is pi by 4 times of theta, because theta is initially 0 and it needs to rise to 90 degree to get a proper measurement of 1, that is the target is found. That's why it's pi by 4 theta rotation is required to get the maximum probability of the quantum state being 0 or 1, representing that the target is found or not found. Now after k iterations, we know the amplitude rises by a factor of sine 2k plus 1 theta, which is simply equal to sine pi by 2, that is 1, showing that yes, the target is found. We can now say amplitude after k iterations is equal to sine of 2k plus 1 theta, which is equal to sine pi by 2, which is equal to 1. See from this diagram, after k iterations it's rising to pi by 2, which is 90 degree. So we can see the total rotation needed for the amplitude to rise up to 1 is equal to sine 2k plus 1 times theta, which is sine of 90 degree. It is 90, sine 90, which is equal to 1, meaning it has risen and found the target. And when it does so, we stop iterating. Now we can see, since theta is in the order of 1 by root n, which we saw it from this relation, and also we saw that after k iterations the angle rises to pi by 4 times of theta, that is k would be approximately equal to pi by 4 times of theta. K is pi by 4 times of theta because 2k plus 1 times of theta is approximately equal to pi by 2. So we can solve for k, which will become 2k of theta plus theta is approximately equal to pi by 2. So 2k times theta will be pi by 2 minus of theta. So k is equal to pi by 2 minus theta by 2 theta. Now if theta is very small and theta is smaller than pi by 2, we can neglect the minus theta in the numerator, which will simply mean pi by 2 times 1 by 2, that will be pi by 4 of theta. That's why we can say k is approximately equal to pi by 4 times of theta. Now if we solve this, we can substitute now in place of theta. We will get something like k would be approximately equal to pi by 4 times the value of theta here would be 1 by root n, which will be equal to pi by 4 by root n, which will be equal to root n 10 times of pi by 4. Now we can simply ignore this as these are constant. In time complexity we don't handle these gets eliminated, so the time complexity becomes big O of root n. Hope you like this proof, and yeah, so this was basically how Grover's algorithm works and root n time complexity. Thanks for bearing with me. I'll see you in the next one. Bye bye.